Welcome back. Now let's dig a little deeper into what is in the innards of a register. Turns out it's called flip-flops. So let's see why they're called that. So what's inside this register? Let's lift the hood on this. So let's give it some names. A register is basically, an n-bit register is basically n 1-bit flip-flops. That's the idea, in parallel. The input is called data, D for data, and the output is Q for, I think we call it quiescent. It means it's stable, quiescent, Q for quiescent. So here is dn inputs, d0 through dn minus 1. Here's n outputs of this 1-bit flip-flop. This clock, which is going to say, this load the register, has to be sent to all of these guys. And this may be the first time to show you, whenever I show a line that isn't connected, I'm going to try to disconnect it there. So that's really important. I'm going to show those lines not connecting. Whenever I show a line that is connected, I'm going to draw a circle there to say it is connected. So if you ever see a line like this, it's really ambiguous. Should it have gone underneath and been a gap, or should have been a circle there? So we're never going to try to do that. We're always going to try to make it very clear which one we meant. So a circle, whenever two lines cross and they meant to cross, it's the same signal just being forked out in a way. There'll be a circle there. If it's ever not connected, there'll be a gap, okay? So just remember that in the future as you see our lines. And hopefully we'll try to have every single drawing we ever show you. So these are called flip-flops, or FF for short, because the name, because it implies that the data is going to flip and flop between 0 and 1. That's the idea. D is data, as Q is output, and also these, by the way, are called D-type flip-flops. The other kinds of flip-flops, there used to be other kinds. D-type is now what we talk about, okay? So D-type flip-flops. So that's how this is going to work. It's N, an N-bit register is N 1-bit, N parallel 1-bit flip-flops. What's the timing? Let's actually go dig even deeper into a flip-flop now. This is important as we start talking about timing diagrams. So this one is going to be called a rising edge triggered. And there's also falling edge triggered flip-flops, but we're going to only consider rising edge triggered flip-flops in this. This is also called positive edge, which means when it goes from 0 to 1, that's when it's going to trigger. It means load, okay? So let's actually read this. So it says, on the rising edge of the clock, the input D is sampled. Remember, here I am. Here's my flip-flop. I'll be a 1-bit flip-flop, 1-bit flip-flop. On the rising edge of the clock, I turn around, I sample, I grab what the input D is, and I transfer it, take some time now, to transfer it to the output. Now it's a 0, turn around, it goes high, okay, load me, clock, go up, now it's a 0. Now I'm a 0, okay, that's what this happens. At all of the times it's ignored. I kind of tried before, it's ignored, the input's changing, I don't care, I'm not looking at you. Only when I'm asked to load, and that rising edge happens, or I turn around and grab the value and have it on the output. That's the idea. So here's an example waveform, okay? Let's take a deeper dive to this waveform now. So I've got a clock, rising edges. Let's look at this, rising edge. So this is the magic time, okay? Rising edge, rising edge. And notice D is changing, right? And D can change all it wants to. Q, I draw like this. This is the way to draw it to indicate, I don't know what it was. It could have been a 1, could have been a 0. I kind of shaded inside of it. It's almost like a filled in area. I don't know what it was before. Unknown. It's like garbage, right? I think of Q as garbage. And only when there's a rising edge do I turn around and grab it. So let's actually take a look. There's my rising edge, and I see a little bit of delay. Remember, there's a delay in all these devices between when I grabbed it, turn around, grab it, and then show it in the outside. So I don't know what it was, but there was, even after this time, I still didn't change it. And only after a certain amount of time am I going to guarantee to have a steady state value of whatever the input was back at the time 0, at that rising edge. And this happens again. If I watch this again, let's keep doing this. There's my rising edge. I sample D. I see the output on Q. Rising edge, sample D, put it on Q, and watch, here's what happens. I even do it if D hadn't changed. Look, D is changing between those two clock guys. Look, D changed in the middle. But from the point of view of the flip-flop, I don't care, because last time I sample it, and now I stay the same. So nothing, from my point of view, I grab it, 0, turn around, D's changing, 1, 0, 1, 0, turn around. If it's still 0, I just grab the 0 and give it again. But I mean, the output should not see it. It'll still be 0 throughout that whole period of that, on the output side. Okay, so far? All right, now this is one of my favorite slides. And we'll stop this lecture series with this slide. The timing is really important to understand these new words. I'm teaching you some new words today. We saw this rising edge triggered flip-flop. We saw that line. Nothing, you've seen this already. This is all from before. This is all from before. Let's actually dig into more detail of this. So the red line is the rising edge of the clock. That's the important red line. And now here's the key. You're gonna say, well, Dan, can D just, while I'm turning around and grabbing it, can D just be moving around? Like, wouldn't you kind of possibly grab a half if it's moving from 0 to 1? And the answer is yes. I could be in a really unstable state if as I'm turning around to grab D, D is changing. So you need to have D stable. How stable? Stable from some time before like negative time before the rising edge of the clock and some stable time after the rising edge of the clock. So in that kind of key window, when I was turning around, D better be locked in. Time before, now I'm grabbing it, and now time after. Better still be stable as I'm grabbing a stable value and having it on my output. So here is negative time. This means we call this setup time. That input D better be stable for the setup time before the rising edge. And here is the hold time. From setup, which is negative time before the rising edge, to hold time after that edge. That better be stable for both of those time windows. And then, so that's two new words. And then, and by the way, input has to be stable in that window, okay? And then there's a delay between when I grabbed it and we saw that on the last slide, the output. We're gonna give a name to it, call it clock, right? Let's see, what should we call the name? The delay is between the clock till it's stable at Q. So it's clock to Q. What should we call it? Clock to Q. So that's what they call it. It's the delay between the rising edge of the clock and when it's stable on the quiescent, calm, quiescent, stable on the output line. So clock to Q delay, okay? 3 names. Setup time is negative time. Hold time is time after from kind of the rising edge till when it needs to be stable. So it's stable between, setup before, hold after, and independent of that, grab it, the output Q is not stable until guaranteed after clock to Q. Could happen before then, but when you go to Fry's Electronics, you're gonna buy a flip-flop. You say, here's some numbers. There's 3 spec numbers, spec numbers in terms of that. And usually they're really small numbers, picoseconds often. And I'm gonna say, well, how about this one? That's the bargain bin. What's in there? Well, that's with a really huge clock to Q delay. Oh, how about that expensive one? Yeah, that's a really small clock to Q delay, right? The faster this thing can operate, the faster you can clock the circuit. So the expensive ones are, and I'm joking about like going to Fry's and getting just a flip-flop, but the point is, it's harder to design a system that has small clock to Q. It's really easy to design one that has a bad clock to Q. So you want to have the smallest clock to Q you want, and also you want to have small setup and hold time. So the window when it needs to be stable is small, and the speed at which I can grab it and have it on the output is really small. So again, you want really small values there for my flip-flop in the ideal case. And again, this is the beautiful block diagram of my DQ flip-flop. That's the end of this lecture. We'll see you at the next one.